My name is Isidro Sánchez. I am going to present on behalf of Alice Soares. The work is entitled Design and Validation of Mixed Mode Device for a Fracture Toughness Analysis of Adhesive Joints. This work has been under the supervision of Professor Raúl Campilho and has been developed in ICEP and INEGI in Porto, Portugal. The presentation is divided in the following topics: introduction, objectives, requirements, preliminary design and design of the equipment, manufacturing of such equipment, validation, and conclusions on future work. Okay, adhesive joints are frequently characterized either in mode 1 or mode 2 using commonly double cantilever beam test or end-notch flexure test. However, in the real-life applications of adhesive joints, they are subject to mixed mode testing. Mixed mode loading. So in this case, it's necessary to characterize the adhesives under this condition. Therefore, many devices have been developed through the years to perform such tests, but problems still exist. So our objective is to develop a new device which allows us to test adhesives either in mode 1, mode 2, or mixed mode. So in this case, we project the device, we create a numerical modeling to validate it before manufacturing it, and test it. Okay, the requirements of the device. First, it should be able to fit inside of a universal testing machine. It should be able to withstand a 20 kilonewton load. Should be easy to manipulate and easy to operate. Should has the minimum possible friction within the components, and should be manufactured in-house. So, as mentioned before, there are many devices that have been developed through the years. Here I present 5 of them. Each one has its own advantages and disadvantages. From these 5, the Fernald and Spelt is the most suitable device from all the tests. And here I present another 4. From these 4 and from the previous 5, the device of Chaves, that is an evolution of the device of Fernald and Spelt, seems to be the most suitable. This was analyzed using a strengths and weakness analysis method. But from that, we established that the device of Chaves, even though is the most suitable, still is a little bit small for the purpose of the test. It has some playing within the components, so it was first created in CAD and evaluated. There is a little problem with this device. Its safety factor is below 1. Therefore, it will yield before the test is complete. So that's not proper. So the main improvements planned for this device is first, increase the length in order to allow longer substrates and longer adhesive joints. To reduce slope or looseness in the fits, calibrated pins were used and rim holes. So in this case, it's a precision device. And some geometrical improvements in order to allow a wide range of mixed mode and single mode testing, as well as reduce playing with the geometry to reduce marking in the samples. This device, first it was proposed a geometrical scheme, And how it works, the mixed mode can be considered as a sum of the mode 1 and mode 2 loads. So in this case, using the superposition principle, we can determine how it's behaving. And if you recall from the previous slides, we have plenty of holes in the device. So in this case, we can manipulate the position of where the load is applied, and therefore we can control the amount of load. Here is the final device proposed, an exploded view. And through a series of iterations, it was improved until our safety factor is above 1. So in this case, the device will be able to sustain the 20 kilonewton load that is a requirement without any yielding in any of the components. So here we are comparing the proposed solution against the original device. So we can see that ours is a little bit heavier, but it's also because it's larger. But it's stiffer, we have less displacement, we have a safety factor above 1, and lower stresses that is expected. The device, as I said, it was manufactured in-house using a machining center. Here I am presenting part of one of the components, this link that joins the upper beam with the specimen. This is the final product showing the calibrated pins. And this is a close-up of the starting of the machining of this component. This little radius is to avoid marking of the samples, and as well, as it has a radius, allow the displacement. So this is a plot of a representation of the whole machining process for one component. Is more or less a standard for all the components. And here we have the final device. These two beams, perpendicular beams, are used as supports. So playing with the position of these supports, we can change mode 1 to mode 2. This is the point of application of the load. The calibrated pins for placing the specimen.
So you have 2 minutes, please. 2 minutes.
I am finished. Thank you.
Okay, thank you.
The device was validated using adhesive joints made of bonded with araldite IB138 and with steel substrates. It was tested in double cantilever beam, so it's mode 1, end notch flexure, that is mode 2, and these two tests that are the combination of are mixed mode. So this is the test. We have a good cohesive fracture, and we can see, for example, in DCB we had more or less good repeatability. In mixed mode, they are quite repeatable. Mixed mode again, quite repeatable, and in mode 2 we have a little difference, but we need to further test in order to draw a better conclusion of this particular case. But in conclusion, the proposed device fulfills all the design requirements. It works. It has been proven that provides accurate results for mode 1 and mixed mode. However, more work is needed for mode 2. As future work, we need further testing and implement some instrumentation to the device.